All right, so this is 14.6b, video 2. So now we're going to talk a little bit about tangent planes. We already know how to do tangent planes by one method, but I'm going to show you a second method. And first I'm just going to show you that it works, and then I'm going to explain why it works. So let's say that we want to find, we'll have this equation right here, xz plus 3y squared minus 4x equals 2. So that's our surface. We want to find the tangent plane at the point 2, 2, negative 1. So there's two different ways that we can do it. All right, so remember that the idea was we can do z minus z naught equals the partial of x times x minus x naught plus the partial of y minus y naught. So let's go ahead and do that. So let's see. In order to do this, I'm going to have to solve this equation for z. So let's see, we're going to get xz equals, I'm going to have to add the 4x and subtract the 3y squared. So we're going to get 2 plus 4x minus 3y squared. And then we're going to have to divide everything by x. So we get z equals 2 over x is the same thing as 2x to the negative 1. 4x over x is 4. And then we're going to get minus 3y squared x to the negative 1. That's dividing everything through by x. We had to do that because we basically had to put this into terms of f of xy. So basically solving for z. Now I can find the partials. So partial with respect to x is going to be negative 2x to the negative 2 plus 3y squared x to the negative 2. The partial with respect to y, the first two terms don't have any y's in it, so we're going to get negative 6yx to the negative 1. And then we have to plug our values in. So we know that fx at 2, 2, I don't need to write the negative 1 since there's no z values there. Plugging in a 2, we're going to get, what was that, negative 2 over 4 plus 3 times 2 squared over 2 squared, so that's 1, so that's plus 3. So we're going to get 3½ there, oh no, excuse me, 3 minus a half there, which is going to be 5 halves. And then fy at 2, 2 is going to be negative 6 times 2 times a half, which is just going to be negative 6. All right, so we have our fx and our fy. Now all we have to do is plug this stuff into the equation of the tangent plane, which is z minus minus 1 or plus 1 equals the partial with respect to x, 5 halves, x minus 2, the partial with respect to y, minus 6, y minus 2. And then if I want to, I can add the 1 over and distribute everything. So we're going to get, let's see, what's that going to be? 5 halves x minus 6y. And then the 5 halves times the negative 2 is negative 5, plus 12 on the right is going to be 7, but I have to subtract 1 on both sides, so we're going to get plus 6. So that would be the equation of the tangent line. There is a second method. So this one was method 1. This one is going to be method 2. And hopefully what you will see is method 2 is just a little bit easier than method 1. The reason being is we don't need to solve for z. Don't need to solve for z. Makes it much easier. So If f of x, y, z equals some constant k, then the tangent plane is going to be the partial with respect to z, z minus z naught, plus the partial with respect to y, y minus y naught, plus the partial with respect to x, get rid of that, x minus x naught equals 0. Put the z up there. Okay, and that's all there is to it. So we want to do that with exactly the same equation up here. So I'm going to take the partial of this with respect to z. Well, that's just going to be x. The partial with respect to z is x. I need the partial with respect to y and the partial with respect to x. So the partial of this thing up here with respect to y first, is just going to be 6y. And then the partial of this equation with respect to x is going to be z minus 4. Z minus 4. Okay, the partials are not too terribly difficult. I do need to plug it in. So this time I got to plug in 2, 2, negative 1. As a matter of fact, let me write that down here. The point was 2, 2, negative 1. So Fz evaluated at 2, 2, negative 1 is 2. Plugging in the 2 value for x. Fy, plugging in the y value is 12. And then Fz, plugging in the z value is negative 1 minus 4, which is negative 5. All right, so let's plug this stuff into our equation. Fz, 2. Z minus z naught, which is going to make it z plus 1, plus Fy, which is 12. Y minus 2. Fx, negative 5. X minus 2 equals 0. So let's go ahead and distribute this and see that it's basically the same thing that we had before. So then we're going to get 2z plus 2 plus 12y minus 24 minus 5x plus 10 equals 0. We need to solve this for z. So 2z plus 12y minus 5x, combine all my constants. 2 and negative 24 is negative 22, and 10 is negative 12. So now we're going to go ahead and solve this for z, meaning we're going to get everything away from the z. So that's going to be 12 plus 5x minus 12y, dividing by 2, we get 6 plus 5 half x minus 6y. Exactly what we have above, written in a slightly different order, but it is the same. So the real question is, why? Why does that work? Well, we're going to show that on the next page. Okay, so we have some kind of a surface, which is kind of the blue part. Hopefully you can kind of see that salmon colored thing is the tangent plane. And then you've got a tangent vector to your curve. So let's go ahead and, first of all, we'll define a couple of things. F here is some function of x, y, and z equaling k. Okay, it has to be in that form. You got to have basically all of your variables on one side and some constant on the other in order for this to work. And you can pretty much make that out of anything as long as you just move all the variables to one side. C, I'm going to highlight C in green. C is this thing right here. So C is on the surface. Yeah, C is on the surface of F. C is also a space curve. meaning that it can be defined as a bunch of vectors, x of t, y of t, z of t. So we can call C r of t. We can define C by r of t, which just basically means that there is some vector coming from the origin out to here, out to here, out to here. Basically, every single possible point on this curve can be defined by a vector. So that would be some kind of x of t, y of t, and z of t. It's a space curve of some kind. So specifically, along C, along our curve C, the function then is going to be defined as f of x of t, y of t, z of t equals some constant k. So what we know is we know that the independent variable here is t. We know that we have intermediate variables of x, y, and z, and our dependent variable here is f. I should put variable, dependent variable is f. So what does all that mean? Well, if I take the partial of f with respect to x times the full of x with respect to t plus the partial of f with respect to y times the full of y, that's a y, with respect to t, plus the partial of f with respect to z times the full of z with respect to t. What we really have here is the full derivative of f, and that would equal 0. So if we set that equal to 0, then this is what we have. This stuff underlined in orange, that's all the partials. That is the gradient. That's supposed to be underlined in orange. Instead, I did it in green. Then we'll do the rest of them in orange. These underlined in orange are actually the full derivatives with respect to t. So the first one is x prime of t. The second one is y prime of t. And the third one is z prime of t. If we take those two things and we dot them, we get right back up to this. But once again, this is the gradient of f dotted with this over here is the derivative of all the different pieces of the function, so it's just r prime of t. And so if you kind of look over here on the graph, r prime of t is this piece right here. Your gradient is that piece right there, which is perpendicular to r prime of t. So this makes sense because the dot product of two things equaling 0 means that they are perpendicular. So let's recall if the gradient of f dotted with r prime of t equals 0, then the gradient of f is perpendicular to r prime of t. And for a plane, if you remember, you need two things. For a plane, we need a normal vector, which is typically a, b, c, and a point. You need a point on the plane. x naught, y naught, z naught. That's what you need to write the equation of a plane. Remember that the equation of the plane was a times x minus x naught plus b times y minus y naught plus c times z minus z naught. Now that's for any plane. Not necessarily a tangent plane, but that's for any plane. Well, since we know that r prime of t is in the tangent plane, the gradient is normal to the tangent plane. So the conclusion to all of that stuff, is that the tangent plane in the form, or excuse me, tangent plane 2, the equation f of x, y, z equals k, is the gradient dotted with the difference between x and x naught, y and y naught, and z and z naught equals 0. Okay, and what I will say is, if all of that didn't make any sense, you can always just go with the fact that it does work, and that's your equation. So this right here is a probably simpler way to go about finding the tangent plane. Let's go ahead and use that fact. So we want to find the equations of the tangent plane and B, the normal line to the given surface of the specified point, at the specified point. So we're given our surface, we're given the point 4, -1, 1. In order to find the tangent plane, this is now really simple. First of all, it's in the correct form. All the variables are on the left, the constant is on the right. So I can do f sub x, which is just going to be, what is that, 2x? F sub y is going to be 4y, and f sub z is 6z. Evaluated at our point, so 2x is going to be 8, 4y is going to be -4, 6z is going to be 6. So that gives us our partials at the point. Plug them into the equation for the tangent plane. So we're going to get 8 times, that's the x part, so x minus 4, minus 4 times y plus 1, plus 6 times z minus 1 equals 0. Now, if I want the equation of the normal line that hits that point, I have the point. I also happen to have a perpendicular vector. That's given to us by A, B, and C. So my normal line, it's been a while since we've written the equation of a line, is x equals, where did we start? Well, we started at 4, because that's the starting point, plus a slope of 8, so 8t. Y starts at -1, and it's got a slope of -4, so -4t. And then z starts at 1 and has a slope of 6t. So that would be the equation of the normal line. So we found the equation of the tangent plane and the normal line that goes through the given point. All right, so let's do example 5. Find the equations of the tangent plane and the normal line to the given surface at the point 1, 0, 0. Same exact idea. So f sub x. Derivative of this thing with respect to x. Well, I guess the first thing we need to do is get it into the proper form, right? Because all the variables have to be on one side, the constant has to be on the other side. So it looks like 1 is going to have to equal x e to the y minus z first. Okay, now we're ready. So f sub x is going to be, the derivative of x is just going to be e to the y. F sub y is going to be x e to the y. And f sub z is going to be -1. So at our point, f sub z is always -1. F sub y here is going to be 1 times e to the 0, which is also 1, so that's 1. And then e to the y, e to the 0 is also 1. So there are our, it's our gradient, it's our slopes. Now we can write the equation of the tangent plane. So the tangent plane is going to be 1 times x minus 1 plus 1 times y minus 0 minus 1 times z minus 0 equals 0. We can simplify this one. That's x minus 1 plus y minus z equals 0. And technically, we can add the 1 to the other side. That would be a very simplified form of the tangent plane. Didn't have to go that far, but I did. And then the normal. Remember, we needed a point, which we have, and we need the normal vector, which is given to us right there. So our normal is going to be x equals starting at 1 with a slope of 1. Y is going to be starting at 0. Don't need to write that with a slope of 1, so that's just t. And z also starts at 0, but it's got a slope of -1, so it is -t. Done. All right, last concept here. Shouldn't take too long to go through. So recall that the gradient of f is in the steepest direction, because remember that the gradient tells you the maximum rate of change. So that, and also that the gradient of f is perpendicular to r prime of t. So if you look at the level curve, which is on the left-hand side, basically that's like looking at straight down at something that has basically the same level all the way around. If you look at the level curve, meaning the height of that orange thing is the same all the way around, if I were to follow it in this direction, all the way around, there is no change in z. dz along a level curve is 0. So dz along a level curve is 0, and that should really make sense. So if you go along the level curve, you have no change of height if it's a level curve. So there's no change in z value. However, in something like the one on the right, what you can see is the steepest curve of ascent is going to be perpendicular to the curve itself. So the blue part here represents the curve. This part right here represents the curve. It was blue, now it's green. But what you can see is it's always perpendicular. Always perpendicular to the changes. So the curve of steepest ascent is always going to stay perpendicular. And the general idea behind that is, think about like water flowing down a mountain. Water is going to find the fastest path down the mountain, which is going to follow the steepest descent down the mountain. I mean, hopefully that just kind of makes logical sense. Water is not going to flow to the left when maybe straight down to the right or something is a much steeper descent. It's not going to go that direction in general. So again, hopefully that makes sense. And if you kind of look at, oh, was that the last page? Oh no, I've got one more. If you kind of look at this last page, this is an actual contour map here of something which is called the Lonesome Mountain. I don't actually know where that is, but you can see the water's path. At every single one of these points, it stays perpendicular to the curve. Excuse me, to the contour. So it's just kind of a general idea when you're looking at a contour map. The quickest way to do it is to find out where the stuff is perpendicular. All right, that's the last concept. Longer video than I expected, but that was it.